Welcome to this model. Today we are going to discuss about error detection and correction. Networks must be able to transfer data from one device to another with acceptable accuracy. For most applications, a system must generate that the data received are identical to the data transmitted. Anytime data are transmitted from one node to the next, they can become corrupted in passage. Many factors can alter one or more bits of the message. So some applications require a mechanism for detecting and correcting errors. Some applications can tolerate a small level of error. For example, random errors in audio or video transmissions may be tolerable, but when we transfer text, we expect a very high level of accuracy. Now, let's first discuss some of the issues related directly or indirectly to error detection correction. Whenever bits flow from one point to another, they are subject to unpredictable changes because of interference. So, this interference can cause or can change the shape of the signal. So, in a single bit error, 0 is changed to 1 or 1 to a 0. In a burst error, multiple bits are changed. For example, 1 by 100 seconds burst of impulse noise on a transmission with a data rate of 1200 bits per second might change all or some of the 12 bits of information. So the term single bit error means that only one bit of given data unit such as byte, character or packet is changed from 1 to 0 or from 0 to 1. Now let's see this example. So here what we see here is the effect of a single bit error on a data unit. To understand the impact of the change, imagine that each group of 8 bits is an ASCII character with a 0 bit added to the left. For example, 000010 ASCII STX was sent meaning start of text, but 00001010 was received meaning line feed. So, single bit errors are the least likely type of error in serial data transmission. To understand why, imagine data sent in 1 Mbps. This means that each bit lasts only 1 by 1,000,000 second or 1 microsecond. Okay. For a single bit error to occur, the noise must have a duration of only 1 microsecond, which is very rare. Noise normally lasts much longer than this. Now let's move on to next concept called redundancy. And almost before that, I want to share the burst error also. So the term burst error means that 2 or more bits in the data bits are changed from 1 to 0 or from 0 to 1. So in this diagram, we can see that the effect of burst error on a data unit. In this case, the first letter here, the letters shown in blue color are changed from 0 to 1 or 1 to 0, right? So now we can notice that the burst error doesn't necessarily mean that the errors occurs in consecutive bits. The length of the burst is measured from the first corrupted bit to the last corrupted bit. Some bits in between may not have been corrupted, and the burst error is more likely to occur than a single bit error. The duration of noise is normally longer than the duration of one bit, which means that when noise affects data, it affects a set of bits. So the number of bits affected depends on the data rate and duration of noise. For example, if you are sending data at 1 kbps, a noise of 1 by 100 second can affect 10 bits. But if you are sending data rate at 1 mbps, the same noise can affect 10,000 bits. Now let's move on to redundancy. The central concept in detecting and correcting errors is redundancy. To be able to detect or correct error, we need to send some extra bits with our data. These redundant bits are added by the sender and removed by the receiver. Their presence allows the receiver to detect the correct corrupted bits. Now let's see the difference between the detection and correction. The correction of errors is more difficult than the detection. In error detection, we are looking only to see if any error has occurred. The answer is simple, yes or no, right? We are not even interested in the number of errors. We just want to know whether there is an error or not. So a single bit error is the same for us as a burst error. But in error correction, we need to know the exact number of bits that are corrupted, and more importantly, their location in the message. The number of errors and the size of the message are important factors here. If we need to correct one single error in an 8-bit data unit, we need to consider 8 possible error locations. And if we need to correct 2 errors in a data unit of the same size, we need to consider 28 possibilities. You can imagine the receiver's difficulty in finding 10 errors in a data unit of 1000 bits. And there are 2 main methods for error detection called forward error correction is the process in which the receiver tries to guess the message by using redundant bits. And this is possible if the number of errors is small. Correction by retransmission is a technique in which the receiver detects the occurrence of an error and asks the sender to resend the message. Resending is repeated until a message arrives that the receiver believes it is error-free, and usually not all errors can be detected. Now let's move on to coding. Redundancy is achieved through various coding schemes. The sender adds redundant bits to through a process that creates a relationship between the redundant bits and the actual data bits. The receiver checks the relationship between the 2 sets of bits to detect or correct the errors. The ratio of redundant bits to the data bits and the robustness of the process are important factors in any coding scheme. Now let's see the general idea of coding. And we can divide the coding scheme into 2 broad categories called block coding and convolutional coding. And now let us see the block coding in detail. In block coding, we divide our message into blocks, each of k bits called data bits. And we add all redundant bits to each block to make the length n equal to k plus r, which you can see in this diagram. The resulting n-bit blocks are called code words. How the extra r bits is chosen or calculated is something what we are going to see now. And for the moment, it is now important to know that we have a set of data words, each of size k, and a set of code words, each of size of n, right? And with the k bits, we can create a combination of 2 power k data words. With the n bits, we can create a combination of 2 power n code words. And since n is greater than k, the number of possible code words is larger than the possible data words. The block coding process is 1-to-1, and the same data word is always encoded as the same code word. This means that we have 2 power n minus 2 power k code words that are not used. So we call these code words are invalid or illegal. Let's see the situation. And now in modular arithmetic, what we use is we use only a limited range of integers, and we define the upper limit called modulus n. We then use only the integers 0 to n minus 1 inclusive. This is modulo n arithmetic. For example, if the modulus is 12, we use only the integers 0 to 11 inclusive. An example of modulo arithmetic is our clock system. It is based on modulo 12 arithmetic, substituting the numbers 0 to 12. So the number 12 for 0, right? In the modular n system, if a number is greater than n, it is divided by n and the remainder is the result. If it is negative, as many n's or as needed are added to make it positive. So consider a clock system again. If we start a job at 11 a.m. and the job takes 5 hours, we can say that the job is to be finished by 16 if we are in the military, or we can say that it will be finished by 4 p.m. and remainder, that is remainder of 16 by 12 is 4, right? Now let's move on to error detection. How can the errors detected by using block coding? And if the following 2 conditions are met, the receiver can detect a change in the original code word. One is the receiver has a list of valid code words. The original code word has changed into invalid one. The sender creates a code words out of data words by using a generator, which you can see in this diagram, that applies the rules and procedures of encoding. Each code word sent to the receiver may change during transmission. If the received code word is the same as one of the valid code words, the word is accepted. The corresponding data word is extracted for use. and the received code word is not valid and it is discarded. However, if the code word is corrupted during transmission but the received word still matches a valid code word, the error remains undetected. This type of coding can detect only single errors, and 2 or more errors may remain undetected. We can assume that the sender encodes the data word 01 as 011 and sends it to the receiver. Now consider some situation. The receiver receives 011, then it is a valid code word. The receiver extracts the data word 01 from it. Suppose the code word is corrupted during transmission and 111 is received. The leftmost bit is corrupted and this is not valid code word and is discarded. Suppose the code word is corrupted during transmission and as 000 is received. The right 2 bits are corrupted. This is a valid code word, but the receiver incorrectly extracts the data word 00. So 2 corrupted bits have made the error undetectable. And as I said before, error correction is much more difficult than error detection. So in error detection, the receiver needs to know only that the received code word is invalid, but in error correction, the receiver needs to find the original code word sent. So we can say that we need more redundant bits for error correction than for error detection. So we can use block coding in error correction also. We can say that the idea is the same as error detection, but the checker function is much more complex. And we can assume, for example, if you assume a data for code word correction, comparing the received code word with the first code word, then the receiver decides the first code word is not the one that was sent because there are 2 different bits. So one of the methods, central concept in coding is Hamming distance. So this Hamming distance is the idea used for error control, and the Hamming distance between 2 words of the same size is the number of differences between the corresponding 2 words. Okay, and the Hamming distance can be easily found if we apply XOR operation of 2 words and count the number of ones in the result. The Hamming distance is a value greater than 0. Although the concept of Hamming distance is the central point in dealing with error detection correction codes, the measurement that is used for designing a code is the minimum Hamming distance. In a set of words, the minimum Hamming distance is the smallest Hamming distance between all possible pairs. So we use d minimum to define the minimum Hamming distance in a coding scheme. To find this value, we find the Hamming distances between all words and select the smallest one. Thank you.